Hello everyone, I'm Marek Modry, your today's host, and this is an online machine learning meetup. It's actually 18th we are doing online, and today we will be talking about voice processing, but before we dive in, I have a few points. As always, we are really grateful for the support from our partners who are Seznam CZ, Konica Minolta, SAS, Rosum, Chiron Hego, DataClaire, and Biano. And if you like this meetup, subscribe to our YouTube channel, which should be somewhere here, and follow our meetup.com profile, Facebook, or LinkedIn. If you want to ask any questions, as usually, we want you to join our Slido, which is URL is slido.com. We will share the link in a few seconds in the chat and also here in the stream. And use there the code MLMU. We will go through the questions you had after each of the talks. And also, if you have any follow-up questions later on, or you just want to meet our speakers, or you want to meet anyone else who was watching the stream with you, join our networking after the session, and you will get the opportunity to meet everyone you want. So our first speaker is Piotr Żelasko. Hello, Piotr.
Hey, how are you, Marek?
Piotr is the Chief Scientific Officer at Meaning, and he will talk about Lhotse, speech data representation library for the modern learning ecosystem. So the floor is yours, Piotr.
Okay, thank you so much.
Presentation.
Yep. First of all, let me say I'm very excited to be here today and share this presentation with you. So first, a few words about Meaning. We are a startup, very recent startup, which is still a little bit in a stealth mode. So I can't really tell you exactly what we are working on. I can just assure you these are some really exciting voice and speech processing applications. And hopefully in the near future, we will be able to share a little bit more news about that. So going to the topic of today's presentation, I am going to share with you some news about a library called Lhotse, which is actually a part of a bigger project that I started during my time at Johns Hopkins University. It's part of a larger framework that's supposed to make speech processing tasks and modeling much easier and more compatible with today's modern deep learning ecosystem. So without further ado, let me start. The number one thing, why would you care about what I have to say in this talk? So I think there are three types of audiences. And audience number one is the one that doesn't really work with speech. So why would that kind of topic be interesting? So for you, I have to say that Lhotse makes speech data much more accessible. If you're working on NLP, which is also sequence learning type of problem, why don't give it a shot? If we make it much easier for you to work with speech, why not try your algorithms? If you're working in general on some machine learning, deep learning, AI algorithms, optimizers, different techniques, why not test it on audio and speech? It's another test case to prove that your stuff works. For the second type of audience works with speech already, but they have other tools that they like. So why do they care? Well, Lhotse is supposed to simplify the data-related part of your work. And some testimonials. Shinji Watanabe, who's the author of ESPNet, which is a very popular speech recognition and speech processing deep learning toolkit, really liked this framework. And he said he's definitely going to endorse it. So there is some buy-in in the speech community already to use those things. Audience number three works with speech, and just seeing the title, they can say, okay, I completely understand you built this. It's every presenter's dream. So a few words about this whole tool, ecosystem or toolkit. As I said, Lhotse is a part of a larger ecosystem. There are two other projects which are called K2 and Icefall. If you are into mountain climbing, you might recognize K2 and Lhotse as the names of the world's second and fourth highest mountains. So this is Himalayan themed. We are actually working with Dan Povey. Some of you might know this name. This is a professor who also worked at Johns Hopkins. He's the chief scientist of speech in Xiaomi right now. And we're basically bringing a lot of concepts from a toolkit named Kaldi, which since 2010 is like the most used toolkit for speech recognition. So we're bringing those ideas into PyTorch and modern deep learning ecosystem. So before we talk about Lhotse, just to get everybody in the audience up to speed about speech and voice processing, let's just quickly review some most common tasks that we encounter with speech. Let's start with classification-like tasks. So here you take any arbitrary recording. It could be an utterance, 5 seconds, 10 seconds of somebody speaking something, and you might want to know who is speaking. So that sort of task is named speaker classification. But there are other classification tasks. You might want to know what is the language in which somebody is speaking, and that's language ID. Or it might not even be speech. It might just be some recording of anything, and you want to know, hey, what's in that recording? And it could be dogs barking, it could be car traffic, or you could say it's speech. And we call that audio event classification. Of course, there's a lot more tasks than these, but these are just some examples. But in the speech world, we're not limited just to classification. There are other tasks that have the sequential nature of speech is not only in the input where you have various lengths of sequences. You might also have that in the output. So for example, you have speech recognition where you want to transcribe the content of what I'm saying. We also call that speech to text. And it requires a different kind of approach in modeling to be able to handle various length of the output sequence as well. Another example of such task is voice activity detection. Let's say in this example, between 0 and 0.4 seconds, there is silence or breathing, which is not speech. And after that, you have speech. And you want to know exactly where those boundaries are. There's also the reverse side of this. So if we have speech to text, we also have text to speech. And this will be the main theme of Jan's presentation, which is going to come after mine. So I'm not going to spend too much time, but this is really, really exciting and cool type of task where you have generative modeling. And there are a lot of ways how you can synthesize that input text into whatever is going to be the recording. I'm not going to say anything more. Wait for Jan's presentation. But just to show you how large variety of tasks we have in speech processing, I'm going to show another type, which is audio to audio conversion sort of. So you have some sort of model. It takes audio in, it takes audio out. And you can imagine like a classic example would be speech enhancement. Let's say my mic is very bad or there's a lot of background noise, and we might want some model to remove that. Also, another example, which might have another input, is voice cloning model, where we take recording of my voice and we want it to sound like Alan Turing, for example. And at the output, we get the same speech, the same content, but spoken with Alan Turing's voice. So after this short introduction, let's move on to Lhotse, and let's start with the core concepts of the library. So we introduced 3 types of abstractions, which are called recording, supervision, and a cut. Recording, think of it as, it could be a very short recording, could be very long recording, it could be one channel, or we could have several microphones, there could be multiple channels. A recording could represent an entire presentation like this. of course, this is not optimal if we think about model training, because we can't really, we don't have unlimited memory. We can't really work with 30 minutes or 2 hours of speech in a single mini batch in training. So this is where actually the cut is going to come in. Cut is going to look into some interesting region of that long recording and produce a single training or testing example out of that. And there's of course supervision, which is a segment in the whole recording which has some interesting piece of metadata related to it. And I will show you more examples later. And here you might see that cuts and supervisions are exactly aligned. This would be the usual case in speech recognition, for example. Each supervision represents some part of a transcript from a particular speaker in the conversation, and we want cuts to be exactly aligned with that. But there is another example where cuts won't be aligned with supervisions, and this could be used for voice activity detection. This way, we have both speech and non-speech area in a cut, in a single training example. So the model can learn to discriminate between the two. So let's look a little bit at the library itself. How does it look on a Python level from a user's perspective? So we introduce a couple of objects in Lhotse. The first one, the core one, is recording. It's just a simple object, really. It's just a bunch of metadata. It might have some ID, some sampling rates, so how many samples per second we have, audio samples per second, what's the total duration, and of course the source. So how do we load it into memory? And here's a little spoiler. Lhotse actually supports a lot of type of audio sources. It could be a file residing on your disk. It could be a URL as well. Oh, the slides jumped for some reason. So we might support, we support also downloading from something like S3 or Google Cloud on the fly. So this really lets you abstract away from where your data is located. You just use a simple function called load audio to get that data. In order for those manifests to be, easy to transfer and work with, we of course support some serialization, and JSON is our format of choice for that. You can see actually the Python class in JSON there, like a mirror reflection, and there's a couple of methods to make that serialization easy. So next type of object is supervision segment. Supervision, as I said before, it is just the metadata. It's the information we often want to model. So that could be the transcript, it could be the speaker identity, the language, it could be gender, it could be a lot of other things too. Let's say we want to do, I don't know, accent detection, or we want to classify, like measure the SNR, learn a model to measure how noisy a recording is. So we can put some custom fields in that supervision segment so that all of our metadata is in one place, and we can transform that to task-specific scenario later. So let's look at some examples. There's a corpus named LibriSpeech. This is the most widely used corpus in speech recognition. It has about 1,000 hours of audiobook recordings, which are cut into like short utterances. And you might see corresponding recording and supervision here. So each recording is a short WAV file, and each supervision is like an entry in a text file. And we just get all of this information together. There's only one channel. There's another type of corpus, which is called GigaSpeech. It's much larger. It has 10,000 hours of audio recordings, which is actually really a lot. It's like the modern, industry scale deep learning type of experiment. And here we have very long recordings, podcasts, YouTube, again, audiobooks. And you might see that supervisions corresponding to a recording, there are many of them, and there are start times which are incremented with each supervision. This is really nice because this allows us to model contextual speech. Let's say we want to, we're building some NLP type of system that processes the output of some speech recognition system. And we might be able to construct contextual training example for learning this NLP system. Cool. So now we're going to Cut, which is really at the heart of all the capabilities of Lhotse. And I am always a little bit scared to use this parallel, but you can think of Cut as a pointer into recording. And I know a lot of programmers hate pointers. I used to hate them too. But this is really, it really points to a particular offset in the recording, and it has some duration and a particular channel. And it might span one or more supervisions. So again, this is the contextual examples that I talked about before. The two major attributes of cuts is that they are lazy. So we execute all operations on the metadata level, and we just update the manifest, but we don't touch the actual audio or feature matrices that we stored somewhere until we load them. So we can chain a lot of operations that you see here together, and only when we actually load the data into memory, we execute them. And if it's possible, we limit the amount of data we read to optimize the I/O. And of course, these operations are composable. And you can see that you can see some examples of them on this slide. Also one really nice thing, we support easy visualization and listening to this audio after all the transform also in Jupyter notebooks. So you can get a feel for your data, like you can listen to it, you can understand what those data augmentation methods are doing with your data. So this is something I'm really always emphasizing, and whether I'm in academia or industry, like the team I work with, like really get to know your data. Otherwise, there are some nasty surprises waiting there for you. And of course, again, these operations are composable and lazy, and we have a lot of unit tests to make sure all of this works as expected. So we take this burden off of you as a user. You don't have to think about these things too much. Again, an example how some metadata processing pipe could look like. The design is inspired a lot by Pandas data frames. And this is really cool. I really like working with this. So we are going to head towards the more deep learning and actual data recipes part of this talk. So before I go into that, I just want to say there are a lot of publicly and like semi-publicly available corpora that you can use for a lot of various tasks, including those I presented before. Lhotse has about 35 to 40 recipes for taking this raw data as it is distributed, as you download it from the internet or obtain from LDC or some other entity that sells this data. And there's a single entry point called prepare name of the corpus, which takes the path to wherever you have the data stored, and it produces Lhotse manifests, which is really nice because it also allows you to combine multiple data sets or like repurpose some data sets that were, let's say, originally intended for text to speech, but now you might want to use them for speech to text or maybe some other task, because you have all this data in a single like common metadata representation. One thing I didn't really say is that in the audio world, it's really a mess. Every one of those corpora that you see on the screen, it comes with a different metadata representation. So traditionally, if you wanted to write some, reproduce the same experiment in a different data set, you would have to put a lot of work into just making everything look common. And Lhotse is also supposed to take some of that burden off of your shoulders. So let's move to how do we actually use all of these things for training. So we have those cuts and CutSets and this nice representation. How do we make that, how do we convert that into tensors? One thing you should know about speech and audio, and if you're working with NLP, you're probably pretty well aware of this, is that because each example might have a different length, it could be a short utterance, short sentence, or long utterance, long sentence. If you naively construct mini batches by just randomly sampling the examples, you will end up with a mini batch that looks with something like on the screen. Those dark areas, dark blue areas, are padding. So this is a lot of wasted computation on your GPU. Like, this is definitely not what you want to do. You want to definitely do something smarter than that. And Lhotse provides its own implementations of the PyTorch abstraction that is called a sampler. A sampler is responsible for selecting examples that go into a mini batch. And one of our samplers is called bucketing samplers. So bucketing is a sort of stratification where you create buckets that contain examples of similar length. And you can see how much computation you're saving here. The padding is minimal. And of course, some batches will have very long examples, some batches will have very short examples, but this is fine. It works in practice. Lhotse also allows you to do some other like interesting stuff. Instead of bucketing, you could try to rearrange those shortcuts and concatenate them together to create longer training examples. It's also another technique how to minimize the padding, but also you can imagine how here this is quite useful for voice activity detection, or maybe another task that we call speaker diarization, which is basically trying to say who spoke when in the recording, like try to find the speaker changes. And this is not something that I've encountered in any of the speech processing frameworks I've worked with in the past. So this is something new. And we also provide some tools for visualizing those mini batches. So it actually helped me a lot with finding some bugs in my data pipelines. How does it work in the code? Actually, it's very, very similar to standard PyTorch data loader thing. We follow the same abstractions. So you use standard PyTorch data loader, and you can use one of Lhotse's samplers. There are many types, and there's not enough time to talk about it, but you can find it in the documentation, which I'm going to provide a link to later. And of course, you have your dataset class, which knows how to map the metadata from a cut into an actual tensor, basically load it, do some augmentations, and so on. One thing to know is that we support dynamic batch sizes. So we specify how much of audio duration we want to have in the whole mini batch. And then the sampler is going to keep adding cuts into that mini batch until it reaches that threshold. It's unlike PyTorch, it's the sampler that actually owns all the metadata. It's not the dataset. The dataset is a little bit like a mapping, like basically a function that takes a mini batch of cuts of metadata and converts that to tensors. Other than that, it's really business as usual. You can just write your training loop or use PyTorch Lightning or some other library that you like. How does it work with multi-GPU distributed training? Well, it works out of the box. You don't really need to adjust anything on Lhotse's side. You just use standard PyTorch distributed data parallel or whatever, and we support all of that. How do we handle really large data? I'm not going to spend time here. I'm just going to tell you there are one or two things that you need to adjust, but it's basically flags or some arguments. And you are able to run your training with really minimal CPU RAM usage. So it's possible not to go out of memory with those really large data sets. Cool. So now you know Lhotse, and what are the first steps to actually adopting it? So you can just install it from pip, or you can use a bleeding edge unreleased version from GitHub. There is a documentation on Read the Docs. It's fairly extensive. Some parts of it could be a little bit out of date, but it's very near the top of my list to update those sections. But if you run into any issues, we're a very open community, and we're very happy if you set up issues on GitHub, and whether it's some issue, bug, question, or you want to add some feature, we're trying to be responsive, and we're very supportful of that. There are some examples on Lhotse website of integrating it with other toolkits like ESP.NET that I mentioned before. And that's it. Well, it's built to make everybody's life simpler, so I'll be happy if you enjoy it. Thank you for your attention. Here are some links to some resources about Lhotse. We have a publication at NeurIPS this year, which you can read. There is also a larger tutorial about the whole ecosystem that was 3 hours at this year's InterSpeech conference. I'm hoping the video will become public soon. And please let me know if you have any questions. Thank you.
So, thank you, Piotr. Let me share the Slido because we have a few questions. Also, feel free to add more during the time Piotr will answer these. So let's start with the first one. May I have multiple supervisions per one cut, for example, for overlapped speech?
Yes, of course. That's a great question. And it's one of the things that when I was building Lhotse, I was thinking like, okay, what are the shortcomings of whatever came before, like whether in Kaldi or ESP.NET or some other frameworks. And overlapped speech was one of those things that I always thought, hey, this is really difficult to deal with those data representations they have. So definitely, we do support that, and even for diarization or something like that, we have ready-made functions that will give you nice like masks showing at which time which speaker is talking and so on. So yeah.
And the second question so far is, what's the license of Lhotse, and is it based on any other underlying library, and what's the core programming language?
Okay, it's a great question. Again, the license is very permissive. It's an Apache license, so you can use it commercially. No worries there. Like Kaldi did that in 2010. It was a great decision, and we're keeping that up. About underlying libraries, so we have a bunch of dependencies for. Of course, there's PyTorch and Torch Audio, which is definitely at the core of the library. There are some other dependencies, for example, for reading audio, or some like HDF5 for storing some feature matrices. I'm striving not to have too many of those, and I might even make some of them optional in the future. But other than that, Lhotse is purely Python. There are no C library parts in itself.
Cool. Awesome. So let's give it a few more seconds because YouTube is a few seconds behind the actual lifetime.
All right.
So in the meantime, let me say, Piotr, thank you for your insightful talk.
Thank you.
It was great, and it's always a pleasure to see somebody who is both researcher, interested in ML, and at the same time, great engineer, capable of building something like that. Awesome. So if you realize that you have any other follow-up question, Piotr will be at the networking after we finish. And so thank you, Piotr, once again. And let me jump to Jan. Hello, Jan.
Hi, Marek. Hi, everyone. Thanks for inviting us. I'm very happy to be here. So,
yes. From some reason, I don't see you.
okay.
Let me. I'm sorry for this. It seems like your camera froze.
Is it still frozen? Okay, how about now?
No, still just a black window.
Okay.
Sorry for the technical difficulties to others in the meantime. Perhaps can you try jumping off the StreamYard and
Yeah, I'll be right back.
yeah. Sorry for this. In the meantime, let me repeat as always that whenever you feel like you could have a talk that you would like to share with others or any topic, feel free to reach out to us. The guys from Meaning is a great example, exactly of a topic that they came up with by themselves. So feel free to reach out to us through the chat here on YouTube, through any of those Facebooks, LinkedIn's, or meetup.coms, or just come to the networking later on and tell me. Cool. Jan, thanks for solving the issue. Jan Weiner will be the second talk. He's an applied research scientist, mainly interested in generative models of speech, including text-to-speech and speech-to-speech, as Piotr already told us during his talk. And he also works in Meaning. And his talk is called Speech Synthesis, Let the Machines Speak. So, Jan, the floor is yours. And
Right. Okay, thanks, Marek. Can you see my screen?
yes.
All right. So let's get into it. So once again, hi, everyone. My name is Jan Weiner, and I'm here to tell you about speech synthesis, also sometimes called TTS for text-to-speech, and what it is good for, how it has evolved over time, and what are some problems that we are facing now to make speech synthesis even better and even more useful. So what is speech synthesis? It's a process of generating spoken audio from text. So speech synthesis systems, you could probably imagine them like some box into which you type your text, and on the output, you can listen to the text read by some machine system. Actually, many of us encounter some form of speech synthesis every day. So do you commute to work by means of public transport? Chances are that the bus or subway announcers were generated by a computer. Or have you ever used a more recent GPS navigation? Then you probably listen to a synthesized voice. So it's all around us. Well, while TTS is successfully being applied by various voice assistants and other devices for machine-to-human communication, it's used for audio content such as podcasts, TV ads, for gaming characters or movie dubbing remains quite limited. But it would be really useful to be able to use speech synthesis in these domains. So, for example, imagine that you are a game designer or maybe a movie director, and you need to record some voice lines for your product. So normally what you would do is you would hire some voice actors and you would spend a lot of hours with them in the recording studio where you would record all those voice lines. But now imagine that instead of this, you would just download some application, you would type down your voice lines, and the application would synthesize those voices for you. You could select different voice colors or emotions, etc., and that would be it. So you would get much cheaper voice acting. If you needed to change some of your existing voice lines, you could just resynthesize them with the same application. There is a big advantage that you could resynthesize them with the same voice and you wouldn't have to invite the same voice actor to the studio twice. if you need to extend something and you need to add more voice lines, you can again do it with the same system. And sometimes there are even scenarios where recording all the voice lines with human actors is quite prohibitively expensive. For example, in open world games such as The Witcher 3, there are like thousands of voice lines for various game characters. So it must have been quite expensive to actually record all the voice lines. And if you could do that with a computer, that would be really convenient. So why is TTS not ready for all these applications yet? So to answer this question, let's take a quick tour through the history of TTS, how it has evolved, where it is now, and what are the current problems, and where it can be potentially heading in the future. So the first attempt to create a computer-based TTS originated around 1950s, and text-to-speech has since evolved into some really awesome sounding systems. The first type of assistant that I'm going to talk about is really simple, and it's called concatenative synthesis. And it works the way that you could probably imagine yourself. So you have a database of some short audio snippets that correspond to some textual units. And what you do is you take your text that you want to synthesize, you parse it into some textual units, and based on those units, you look up those audio snippets in the database. You have those audio snippets, you concatenate them together, and you receive the final synthesized audio. Here's a simple example how this could be achieved. So this is our database. We have those 4 text tokens, and we have corresponding audio units. Let's listen to how they sound.
L O.
So let's say that we want to synthesize the word hello. We parse it into those text tokens, and we concatenate the audios together, and that's it. And it sounds like this.
Hello. Hello.
As you can hear, there are quite many problems on the boundaries between the audio units. And it has very unnatural intonation and sounds quite robotic, and it's just quite hard to understand in general. Of course, this is a very simple model, and in reality, you would have a database where you would have quite many audio units for each of those tokens. So you would have many versions with quite slightly different intonations and slightly different ones, different lengths of them, for example. And you would use some statistical models to select the best audio units in the given context. And it of course, makes the system sound a bit better. Another system or another approach is called Forman synthesis. And it uses the fact that the human vocal tract can be quite well modeled by a source filter model. So what it does is it takes a white noise signal plus some impulse signal. It combines them together and synthesizes speech. It uses signal processing techniques to do that. And it uses the fact that the vocal tract has quite easy to distinguish response to the signal. So that's how it's done in very simple terms. And there's a library called eSpeak, which actually uses this technology. You can it's freely available. You can download it and you can synthesize your own lines. So I did that, and it sounds quite good. And it has many controls. So you can synthesize a male voice that speaks slowly.
What's the meaning of life?
Or it can speak quite fast.
What's the meaning of life?
It can whisper.
What's the meaning of life?
And you can also synthesize female voice or even a different speaker.
What's the meaning of life?
As you can probably hear, it does not suffer as much with the boundary effects of the previous method, but it's still quite robotic. It also does not have human-like intonation, and it's in general quite distinguishable from humans. So let's get to some more recent stuff. So as with many other problems, deep neural networks took speech synthesis by storm and improved the quality quite drastically in the last couple of years. These systems usually accept a text-based input, and they directly output either audio or they output a spectral representation of audio that further gets vocoded into the audio what you actually hear. These systems are many times end-to-end, which means that you have a simple box. You just feed some data into it and you train the model and it just starts doing, hopefully, what you want. So the only things that you need is computational resources. You need the model itself and you need text and audio pairs for your data, and you should be good to go. And the audio should be of a good quality if you want the system to sound good. So let's listen to some examples how these systems sound.
He has read the whole thing. He reads books. Peter Piper picked a peck of pickled peppers. How many pickled peppers did Peter Piper pick?
So it's much better than before, right? There are no boundary effects. The voice is nice and smooth. There is no robotic sound in it. The intonation sounds also quite natural. It has human-like phrasing and generally sounds quite well. It can even do like tongue twisters and yeah. These samples were taken from a Tacotron 2 system, and you can listen to more of them on the link below. So it seems like TTS could be a solved problem by this, right? Well, it turns out it is not. And why is it so? Well, modern systems are quite good for announcing, reading of instructions, and for similar tasks that do not require too much emotional engagement of the speaker. So they usually speak in this calm voice, they announce you something, and that's pretty much all that they can do. But imagine that you want to apply this to some conversational setting. The results could sound quite unnatural, right? For example, in the TTS output, there are missing hesitations that are common for humans. There are missing filled pauses such as and also the intonation of those systems usually does not correspond very well to the surrounding context. So if you just place this voice into a random conversation, it's probably going to sound a bit off. So that's conversational speech. Another thing is high expressiveness. For example, imagine that you have a horror movie, you are a movie director and you want to synthesize voice lines for the actors. And imagine that the actors in the horror movie speak with this like Alexa assistant kind of voice that is very calm. It would just not make the movie very good, right? So we couldn't use it. And another thing is that it's not very good at cloning voices of unseen speakers with limited number of reference recordings. We'll get to that later, but let's just keep it in mind for now. So we'll just now run through a couple of examples of how these problems are being solved right now. So let's get to the emotional text-to-speech. So these samples that I'm going to play in a second were taken from emotion controllable speech synthesis using emotion unlabeled dataset with the assistance of cross-domain speech emotion recognition. And so there is always a reference. It's read by a human. There is a label of an emotion that it's supposed to represent. And then there is the synthesized variant that was synthesized by their system. So let's listen to them and see how well it works.
For a long interval, the two girls faced each other across the ruined garment.
I never get up early on Sundays.
But however, there is no occasion to trouble you.
I never get up early on Sundays.
So that's relatively sad. It works quite well.
Nobody has any right to take it from me when I care about it and they don't.
I never get up early on Sundays.
And this sounds a little bit more annoyed than angry.
Aye, that is very pretty talking, but it won't do. The doctor is the man I see.
I never get up early on Sundays.
And this one is just weird. So as you could probably hear, not always do the resulting audios map well to the corresponding emotions they are supposed to represent. Also, the audio quality is a bit worse than the reference. In some cases, it's much worse than the reference. And yeah, it's just not something that we could already use in movies or in some real products. So there's the problems that are with emotional TTS is there is not that much data that we could use for training of our systems. There are usually missing labels, and there is just not enough audio, labeled audio. The other thing is that the models sometimes have problems modeling of those emotions because every speaker is quite different when they express their emotion, and the model has to learn to somehow express the emotion differently for all those speakers. So it's quite a difficult task. Yeah, so let's go to the next problem. It's multilingual TTS. So most of the current speech synthesis systems are unilingual. That means they usually speak English. The problem is, if you want to use it for a GPS navigation and you want to travel to some foreign country, the system is going to read all the city names and all those foreign words incorrectly. For example, this is a sample. This is a sample from an English TTS, how it sounds on English.
This is really awesome.
And this is how it sounds when it tries to read German.
It's spreche keen-doost.
So it probably did not read any of those words correctly. So what to do with it? So one of our colleagues, Tomáš Nekvinda, worked on a multilingual TTS system, and his system is able to synthesize a sentence that contains German, but also, for example, Russian or Chinese words, and it works really well. So let's listen to how a German sentence containing some Russian words sounds like.
Der Kreml ist das wichtigste Bauwerk in der Nischni Novgorod Altstadt.
So Kreml sounds quite close, and Nizhny Novgorod sounds good to me. And let's listen to Chinese.
Geboren in der Provinz Sichuan, war Deng Xiaoping unter den ersten chinesischen Arbeiterstudenten.
So this, with a little bit more work, this could be really useful for GPS navigations. If you want to listen to more examples, definitely visit Tomáš's project. It's really awesome. All right. So the next problem is, as I mentioned, zero-shot voice cloning. So what it is? So you have a voice actor. You let her record, for example, 5 samples, 5 sentences with her voice, and then you take a text-to-speech system. You show the system those voice examples, and then you expect the system to speak like this voice actor or this voice actress that was in your studio. This turns out to be quite difficult, and there is a project called Cocky AI. They do some awesome projects with speech synthesis, and they recently released a zero-shot voice cloning model. So I tried it. I recorded my voice as a reference, and then I tried to synthesize some sentences. So let's hear how it sounds like. This audio serves as a reference for voice conversion.
And this audio should clone my voice. I wish I sounded like this.
Yeah, so to me, it doesn't sound like me. It's relatively close. It's a male voice. The age would probably be similar. It speaks with similar pitch, but the timbre is a little bit off, I would say. But it's really good. It's definitely a good progress. All right, so these were some of the problems and some showcased how it works right now. And now I'll just spend a little bit more time talking about the future of TTS. So one thing that could really help, and that started to appear also in other areas of research, is multimodal systems. So let's say that we want to synthesize some lines, some voice lines for a movie scene with multiple actors in the scene, etc. So we have the transcripts, and we have a system that can synthesize that. We would like to also have, the audio should be lip synced with the actors, and the emotions should match the actual scene. So it's really difficult to do that just from the text. But what we can do is we can show our system also some more information, for example, the video from the movie, or we can provide some meta information about the actors. So we can give their age, we can provide some sort of relationship among the actors or the characters that are playing. Or we could provide, for example, the summary of the whole text to be read, or the summary of the whole movie, so that the system knows what's the overall theme. This would definitely, it would hopefully help with lip syncing, etc., and could make conversational text-to-speech, more, how to say it, achievable. The other area is controllable systems. Think of it like Photoshop for speech. So let's say that we have some pretty good models. They are able to synthesize nice emotions, and they just sound great. So how should we interact with these models? And how could we use them for post-processing? So this would be really useful for some audio engineers or for some movie post-processing in the studio. So we could, for example, have some sliders for emotion control of the synthesized speech, or we could have some intonation and phrasing control either by, touchpad or by the audio designer's own voice, for example. I don't know what the good interface should be, but it would be really interesting to see some experiments, and this is probably going to get better and better over time. Also, another feature could be voice in painting. So imagine that you have a voice line recorded by an actor, and you want to change the script. You need to change one particular word. For that, you would have to invite the actor to the studio again. But with the Photoshop for speech or something like that, you could just cut out this word and replace it by a synthesized word, and it could sound natural. That would be really useful. And then there is multi-language voice cloning. So this is in a scenario where the system clones your voice color or your voice timbre and synthesizes speech that sounds like you, but in a different language. This could be super useful for international conferences. So imagine that you have a conference, and you have a system that automatically transcribes what you're saying and automatically translates it into another language. Now it's being done by human translators. So if we have a fast enough system that is able to clone your voice properly and speak in another language, we could do this automatically, and it could just bring international communication to a whole new level. All right. That's it from me. Thank you for your attention, and I'm looking forward for your questions. Thanks.
Awesome. Thank you, Jan. Let me just quickly open the screen with the questions. That should be pretty publicly. And here we are. So how do you measure text-to-speech quality? Do you evaluate it usually by listening to the resulted speech, or do you have some automatic reliable metric?
Well, that's a really good question. And so what we usually do is we do human tests. So we collect or we synthesize maybe 10 or 15 audio files, and we make a survey. And we invite maybe 10 or 20 participants to the survey, and they listen to audio synthesized by our system. And they can also listen to audio synthesized by some other systems or to some reference recordings recorded by humans, and they give scores. And based on the relative scores of the survey, we can tell if our system is an improvement over some baseline or not. So that's how you would do it with human surveys. And but you can also, there are also some experiments with automatic metrics that are trying to estimate the scores from those surveys just from the audio data. But it's open area of research.
Cool, thanks. Yeah, we also have this answer that's related as a question. It's the similar thing that you just said, that there is also automatic way how to do the evaluation. I will copy paste the links to the main chat in a couple of seconds. And in the meantime, there is the third question. In natural language processing and image processing, there are races over who has more complex model. For example, GPT-3. Is there something similar happening in speech synthesis?
So races over who has a more complex model, like GPT, like who has the bigger one. I would not really say that's the case in speech synthesis, because you can usually have a pretty small model in terms of number of parameters and still have it sound quite well. I would say that there is more interest in evaluation of TTS, in emotional and conversational TTS, and in those areas that just make it more useful for actually marketable products.
Great. And in the meantime, we have another question, which is, are you aware of IBM Watson text-to-speech? If it is not a secret, can you tell us how is your model different?
So, so to be clear, in this presentation, I didn't describe any of our models or anything. These were just general models that you can find on the internet. So I don't know what should I answer to this.
So perhaps is there any general direction that you are taking in your work which is different to how you know or assume that IBM Watson could be working?
It's really something that I cannot answer.
Cool, yeah, that's understandable. Great, so let's wait a few more seconds again to see whether there will be somebody else coming to the party with the question. Other than that, let me say thank you. It was a great and insightful presentation, and thank you for all those examples that you had in the presentation. And before we get back to the question that we got in Slido, I just wanted to remind everyone who is listening that we will continue at the networking, which will happen at wonder.me platform, which is a video call platform where you can move around in the space and pick who you want to talk to. So we will share the link just after the session so you can join, and Jan will be also there to answer some of your follow-up questions if you have any. And now let's get back to the questions. Do you ever wonder if such technology could be misused?
Oh yes, quite often. And you can misuse it by yourself. If you go to some publicly available projects, you can just download them, play with them for a couple of days, and you should be able to replicate somebody's voice, etc. So there's definitely space for misusing of these technologies, but there is also research that is trying to fight that. And there are actually some models that are doing like speaker ID, and they're trying to tell if the audio is synthesized or not, or if it's your voice or somebody else's, etc. So it's the same like with images and with guns and deepfakes. It's similar in principle also with synthesized speech.
Mm-hmm. Great. I'm wondering, have you ever noticed, is there any initiative to, I don't know, watermark the synthesized recordings that are generated, I don't know, from those tools or something like that, so that it is easy to detect it when somebody misuses it?
Like I don't have anything specific in my mind right now, but for example, if you could hear the in one of those samples that I played from Cocky AI, they just simply watermark it by playing audio on top of it, like music.
Mm-hmm. Yeah. Awesome, thanks. So that's it. This is the end of our talks. Thank you, Piotr. Thank you, Jan, for both your talks. Let me bring Piotr among us. And I just wanted to say that it's not like that all the companies will have just one slot. So if you ever have any follow-up on your talks, feel free to ping us again and come back, because I guess that we will be curious about your progress. And there is an option for you to quickly say anything as a conclusion if you want. I don't know, you are hiring, you are not hiring, you have a website perhaps, because when people search for mention, that's fun.
Well, Marek, we are definitely always looking for talented people. So if you are interested, and we didn't say what we're doing yet, but based on these two presentations, I'm hoping you can tell it's definitely something super exciting. So if you are interested, please drop us an email at job@meaning.team. I'm gonna write that somewhere in the comments.
I'm sharing my screen with the email. Yeah.
Awesome. Oh, perfect. Yes, that's exactly that email address.
Awesome. Great. So thank you again. And for everybody else, thank you for watching the meetup today. We hope we will see you soon again. Check our meetup.com profile. That's the place where we tend to have the most up-to-date schedule and the program. And as I said, if you want to join our team, or you want to just have a talk or ask anything, or connect to anyone, reach out to us and we will get back to you. So see you in a bit at the networking, which is at the URL that I'm just sharing. And we will also share the link to the YouTube chat. And see you in a bit.